Welcome to this explainer from Forge College. You ever find yourself writing the same exact logic over and over again, but for slightly different types in your Rust code? Well, today we're diving into one of Rust's superpowers for writing clean, reusable, and just incredibly flexible functional code. This one's for you.
Okay, let's dive right in. I want you to imagine you have two separate islands in your codebase. Over on one side, you've got the neat and tidy, predictable isle of structs. And way over there, you have the wild, super flexible isle of closures. Now, you need a function, a road really, that can handle traffic from both of these islands, but without you having to build two completely separate highway systems. So, how do we build that bridge? Especially when you're building on-chain programs, where clean, predictable code isn't just a nice-to-have, it's absolutely essential.
You know, this really highlights a classic problem in programming. How in the world do you apply the exact same behavior to completely different kinds of types without just copying and pasting your code all over the place? Because that just leads to bugs, it's a nightmare to maintain, and, well, it's just messy. We've got to find a way to bridge this chasm.
So yeah, on one side, you have your structs. They're named, they're well-defined containers for your data, super predictable. And on the other side, you've got closures, those awesome anonymous functions we talked about last time that can grab variables from their environment. They are both insanely useful, but right now, a big old chasm of code repetition is keeping them apart.
So, how do we bridge this gap? Well, you don't start by just pouring concrete, right? You start with a blueprint, a design that describes what our bridge needs to do without getting bogged down in what it's made of just yet. And in Rust, that blueprint has a name. It's called a trait.
A trait is basically a contract. It's an agreement. It says, hey, if you want to use my bridge, you must have this capability. It doesn't actually do anything on its own, it just defines a shared behavior, like, say, the ability to transform a number.
And check this out. What's really cool here is just how simple our blueprint is. We're creating a trait, we're calling it transform, and the contract only has one rule. You have to provide a function named apply that takes an integer and gives back an integer. That's it. That is our entire blueprint. Simple, right?
Okay, with the blueprint ready, we can build our first on-ramp. We're connecting our isle of structs. Here, we are explicitly implementing the transform trait for our add-end struct. We're basically telling the Rust compiler, hey, I promise this add-end struct fulfills the transform contract, and then we provide the apply function to prove it.
Okay, so one on-ramp is built. Our struct can now get on the bridge. That's great. But what about the entire isle of closures? I mean, there could be hundreds, even thousands of different closures in our code. Are we really going to sit here and build a brand new on-ramp for every single one?
No way. That would be completely impossible, not to mention a total nightmare to maintain. There has got to be a better way. And luckily for us, Rust has this little bit of magic up its sleeve for this exact problem.
And this right here, this brilliantly illustrates the solution. It's called a blanket implementation. This one piece of code acts like a magical blanket that just covers the entire isle of closures. Since all the closures that fit our needs already implement a built-in trait called fn, this single implementation automatically builds a bridge for all of them, instantly. It's just beautiful.
All right, so our bridge exists now, and both of our islands are connected. We now have two main ways to write functions that can use it. You can think of them as two different kinds of vehicles that can cross our bridge. You've got generics, and you've got trait objects.
So, the really crucial point here is the trade-off. On the left with generics, the compiler creates a specialized, super fast version of your function for every single type you use it with. It's what we call a zero-cost abstraction, and that's a total game changer for Solana development where every single cycle counts. On the right, trait objects give you way more flexibility, but there's a tiny performance cost because the decision about which code to run happens when the program is running, not when it's compiling.
Let's use another analogy just to make sure this really sinks in. Using generics is kind of like having a set of perfect custom-made cookie cutters. You get a perfect, totally optimized shape every single time. A trait object, on the other hand, is more like an adjustable wrench. It's incredibly flexible, and it can handle a bunch of different jobs you throw at it at runtime, which is perfect for when you need to, say, store a bunch of different types together in one list.
So, what does this all mean for your own coding toolkit? Especially when you're building complex apps on a blockchain like Solana, where performance and flexibility are just absolutely key.
It means you now have this incredibly powerful pattern at your fingertips. You can define a shared behavior with a trait. You can use a blanket implementation to instantly bring all your compatible closures into the fold. And then you get to choose between high-performance generics or super flexible trait objects to write functions that can accept both structs and closures interchangeably. This is really the key to writing truly abstract and reusable code in Rust.
This is a fantastic pattern. It's so powerful. But as we solve one problem, we usually uncover the next level of complexity, right? Our bridge works great for simple data, but what happens when our closures and structs aren't owning their data, but are just borrowing it? How does the compiler know that the data they're borrowing is going to live long enough?
Well, in our next explainer, we're going to dive headfirst into one of Rust's most famous and most powerful features, lifetimes. We'll see how they help us build even more robust and reliable bridges in our code. To learn more about Rust, Solana, and a ton of other Web3 topics, go visit forge.college. Thanks so much for watching, and happy coding!